Welcome to AI Explains. Imagine you have a time machine, but instead of, going to see dinosaurs, you crank the dial all the way back,
Yeah.
like 13.8 billion years back to the very first moment the universe was born. That's basically what we're talking about today.
It really is the ultimate time travel story. We're doing a deep dive into a paper from the BICFT2 collaboration, and this was a team of scientists camped out at the South Pole with this huge telescope. They were trying to snap a baby picture of the universe.
And not just any picture. They were hunting for something specific, right?
Yeah.
Evidence of inflation.
Exactly. So for anyone scratching their head, inflation is this idea that right after the Big Bang, the universe didn't just expand, it exploded. I mean, it went from tiny to galactic in, well, less than a blink.
A growth spurt faster than the speed of light.
That's it. But proving it is incredibly hard. You can't just point a camera at it. You have to look at the afterglow of the Big Bang, which we call the cosmic microwave background.
Okay, the CMB. That's the leftover heat from the explosion, still glowing out there in space. But what were they looking for inside that glow?
They were looking for ripples. The idea is, if the universe really expanded that violently, it would have literally shaken the fabric of space-time. We call those shakes gravitational waves.
So it's like throwing a huge rock into a pond. You get these ripples spreading out.
A perfect analogy. And they were looking for the cosmic version of those ripples, frozen in that ancient light.
And how do you see something like that?
Through something called polarization. Light waves wiggle in different directions, you see. BICFT2 was hunting for a very specific twisting, swirly pattern in that light. It's called B-mode polarization.
Think of it like a fingerprint then, if they found that specific swirl.
It would be the smoking gun, the first direct proof that inflation actually happened.
So the big moment. Did they find it?
They did. That's the thing. They found it. The team analyzed all their data from the South Pole, and they saw those exact swirls. It was massive news. They basically announced, we've found the ripples from the beginning of time.
Wow. I mean, that's a Nobel Prize right there. But
I get the feeling there's a pivot coming. You mentioned a note added at the very end of their paper.
right. The problem was what we call foreground.
Mm-hmm.
To see the deep universe, you first have to look through our own galaxy, through the Milky Way. And our galaxy, well, it's full of dust.
And we're not talking about the dust bunnies under your couch.
No. Interstellar space dust. And here's where it gets tricky. This dust is magnetized. So the little grains of dust, they all line up with the galaxy's magnetic field.
Okay. And because they're all lined up, when they glow, they give off light. That's, let me guess, polarized.
Precisely. The glowing magnetized dust in our own galaxy creates a swirly B-mode pattern. A pattern that looks almost exactly like the one they were looking for from the Big Bang. Oh no. So the telescope saw the swirls, and the data was correct, but they might have just been looking at, a dirty window.
That was the fear. The BICP2 team had used older models that said, don't worry, that part of the sky is pretty clean. But then the Planck satellite released new data, much better maps of the galaxy.
And I'm guessing those maps showed the window wasn't clean at all.
Far from it. The new data showed the dust in that exact spot was much brighter and more magnetic than anyone had thought. Once they crunched the numbers again, it turned out the entire signal could be just local dust.
So it wasn't a picture of the dawn of time. It was interference from our own galactic neighborhood.
It's like spotting a monster on the horizon and realizing it's just a smudge on your sunglasses.
Exactly. And it feels like a disappointment, but it's really not. This is a huge win for the scientific method. Science is all about checking and rechecking and being willing to be wrong. BICP2 found a real signal, and that pushed everyone to understand our own galaxy better than ever. It really shows you can't just find the data. You have to understand everything that's standing in the way of it.
That's the lesson. We now know that to see the dawn of time, we first have to figure out how to mathematically wipe the dust off the window.
Which leaves us with a pretty big question for you to think about. If the dust in our own backyard is enough to fool our best telescopes, what kind of new technology will we need to finally wipe that window clean and see what's truly hiding behind it?